What we see here is a video of me in my younger days sporting a really nice sweater vest throwing a tennis ball. Welcome to Hovercraft Physics and Chemistry for a video about projectiles. The purpose of this video is to understand the physics that underlies projectile motion. A projectile is any object that is launched or thrown through the air and then acts under the influence of gravity only. We'll assume here that air resistance is small enough that it can be ignored. And what I've done is set this up so it'll show us every 1/10 of a second once the ball is launched. The ball has just left my hand and it's going to move from left to right. So this could be considered time 0, time 0.1 seconds, 0.2 seconds, 0.3 seconds, 0.4 seconds, 0.5, 0.6, 0.7, 0.8. In a previous video, I showed how we could analyze this data using an online app called JSTrack to track the motion of the tennis ball. This graph is the horizontal position versus time graph. What should jump out at you right away is that it's a linear relationship. Again, this is only tracking the left to right motion of the ball. Because it's linear, we know that the ball is moving with constant speed. The trend line I get from Google Sheets is right here. Translating that into a position versus time model, we have a slope of 2.5 meters per second. That slope represents the constant speed of the tennis ball as it moves from left to right. If I were to translate that into a velocity versus time graph, it wouldn't be very interesting. The horizontal velocity stays constant at 2.5 meters per second. We should think about why that's true. When an object moves with constant velocity, that means either there's no force on the object or there are balance forces with a net force of 0. In this case, once the ball leaves my hand, I'm no longer pushing it, I'm no longer exerting a force on it, and gravity only acts in the downward direction. So gravity isn't going to cause an acceleration in the horizontal direction. In the vertical direction, however, we will see acceleration. This is the position versus time graph for the vertical direction, tracking the up-down motion of the ball. We see that it's a quadratic relationship, and I've used the trendline tool to find the mathematical model for the motion. One of the things I don't like about Google Sheets when it analyzes quadratic relationships is that it lists the terms in reverse order. In math class, you probably learned that a quadratic function has the form y equals ax squared plus bx plus c. I was a little bit worried that maybe this has changed since I learned it, so I Googled it, and according to Google, it should be in the form ax squared plus bx plus c. So Google's going against their own featured snippet in this case, but we'll go with it. So we'll try to make sense of this quadratic model and how it is applying to the motion of the tennis ball. Again, keep in mind, the trend line as listed here is in reverse order. The easiest way to make sense of this equation is to think about the general equation for position versus time for accelerating objects. We can use this equation as a guide to make sense of each of the coefficients. This is the properly written equation plugging in the values from the trend line. The first term represents 1/2 a, meaning half the acceleration. So the actual acceleration based on this data is -10 meters per second per second. It's not perfect, but it's pretty much equal to acceleration due to gravity, -9.8 meters per second per second. It's only a 2% error, and it gives me a nice round number to work with. So from here on out in the video, we're just going to assume that the acceleration is -10 meters per second per second. Keep in mind, this data is only tracking the up-down motion of the ball. The second term coefficient represents the initial velocity. When it was thrown, it was moving upward at 4.0 meters per second. The last term is the initial position of the ball. The ball started about 0.51 meters above the table. I set the 0 position equivalent to the table. Let's take a moment to consider what happens to the vertical velocity as time passes. It's not as simple as the horizontal velocity, which was constant at 2.5 meters per second. What I've set up here is a data table where I can do some calculations to consider what the velocity will be in each subsequent frame of the video as I increase in time by 1/10 of a second every video frame. I know that I started with an initial upward velocity of 4.0 meters per second from the mathematical model that I just explained. The general equation for velocity under a constant acceleration is acceleration times time plus the starting velocity. What I've done in the spreadsheet is entered this general equation in terms of what I know is true for this particular case. The acceleration is -10. Again, I'm using the round number for acceleration due to gravity. I need to multiply that by the time value, which in this case would be located in cell A4, and then I need to add in that initial velocity term. When I hit enter, it calculates the value for me. Again, we have some nice round numbers to work with here. In 1/10 of a second, it's going to lose 1 meter per second. If I drag that formula down to the rest of the time values, we'll see that the trend will continue, and we can also see the data points plotting in the graph. At 0.2 seconds, the velocity has dropped to only +2 meters per second. A tenth of a second later, it's slowed down to 1 meter per second. A tenth of a second later, it's going to be moving downwards. At 0.4, the velocity is 0. That's the vertical velocity. It's when it hits the peak. It's not moving up or down at that instant. 1/10 of a second later, it's now moving downward. And because the acceleration is negative, I keep decreasing the velocity by 1 meter per second every tenth of a second. At 0.6 seconds, now we've noticed that the velocity values have gone below 0. They're becoming more and more negative. That means the ball is speeding up and moving downward. And we see that trend continue until 0.8 seconds. The velocity at that time is -4.0 meters per second, or a downward 4.0 meters per second. Just so we can review it again and compare, this was the horizontal velocity versus time graph. It was constant and 2.5 meters per second. The vertical velocity graph shows that the velocity is changing steadily at an acceleration of -10 meters per second. So how do we make sense of these velocities in terms of the flight path of the ball? I've gone back to frame 0. This is 0.0 seconds. We know that the horizontal velocity is 2.5 meters per second at this point. In fact, it's constant. That vector will never change because there's no force in the left-right direction to cause it to accelerate. In the upward direction, from the mathematical model, we know that the starting velocity was +4.0 meters per second. So the ball is moving at an angle. We can represent the angled velocity of the ball by geometrically adding the x component and the y component of the velocity. The geometric sum of those two vectors looks like this. That's the angled velocity that I threw the ball at. It's moving to the right, it's also moving up, and we can see from the length of the vectors that it has a little bit more upward motion than rightward motion at this point. Let's see what happens in the next frame. Notice that the horizontal velocity is the same. The vertical velocity is now less because gravity is acting on it in a downward direction. It's slowing down in the vertical direction, but it's keeping a constant velocity in the horizontal direction. In the next frame, we'll see that that will continue. So again, the vertical velocity vector component is shorter. The horizontal vector is the same. It's still moving at an angle, but it's not as steep. Now we've almost reached the peak. The horizontal velocity, again, is unchanged. Gravity has caused the vertical component of the velocity to become quite small, and we'll see in the next frame that it actually goes to 0. When we reach the peak, we still have rightward motion, but there is no upward component to the velocity. In fact, the velocity vector is exactly equal to the x component at this point because there is no vertical velocity at the peak. Let's see what happens next. Now the ball is moving downward. The vertical velocity component is negative. It's small because it hasn't had a lot of time to speed up. The horizontal component is still the same rightward value, 2.5 meters per second. As it falls, the vertical velocity vector will get bigger and bigger, pointing downward. We'll see that here, here, and here. Notice that the vertical component to the velocity got bigger and bigger, and again, that key fact that the horizontal velocity is constant. If we want to run through that and look at things a little bit more quantitatively, I've added the time value for the frame, the x velocity, and the y velocity. I'm also showing the speed, so that would be the angled speed of the tennis ball at each point. Maybe you're clever enough to figure that out. It'll take some geometry. Let's see how those values change in each frame. At launch, the speed is actually 4.7 meters per second along the angle shown by this vector. Each frame will see that the y velocity decreases by 1 meter per second. The x velocity stays constant. The speed gets smaller as well. Now the y velocity is only 2 meters per second. Now the y velocity is only 1 meter per second. And again, we reach that peak point when the speed is equal to the x velocity, because there is no y component to the velocity at this point. As the ball moves downward, we'll see that the y velocity will become negative. We also see that the velocity vector, the sum of the vertical and horizontal components, becomes more and more angled downward as time passes. We'll also see the y velocity change accordingly. So we reach the point that the ball has come back to its launch height. We see some things that are equivalent. The x velocity was always positive 2.5 meters per second. It steadily gained ground from left to right by 2.5 meters in a second. The y velocity changed. It has the same magnitude as it did at launch. It's just negative now because it's on its way downward. It's important to notice that there is some symmetry around that peak point. That can help you when you start to solve problems involving projectile motion. You might think we're done, but I have a bonus. I recorded the next frame, and the ball is now below the height that it was launched. Look at what happened to the y velocity. It still decreased by negative 1 meter per second in that frame. The y velocity vector got even bigger, and again, the x velocity stays constant at 2.5 meters per second. The speed has increased as well to 5.6 meters per second in the direction shown by the velocity vector. Thanks for watching.